Hey everyone! Let's start with a simple question. Have you ever wondered where all the energy of a gas actually sits? I mean, when you heat air, what exactly are you heating? Well, it's not the air as a whole, it's the individual molecules whizzing around inside it. Each molecule is a tiny particle of energy in motion. Now, for a single molecule of mass m moving in three directions, its total kinetic energy is half m times the sum of Vx squared, Vy squared, and Vz squared. In thermal equilibrium, that means when everything is nicely mixed and balanced, the average energy per molecule comes out to be 3 by 2k times T, where k is the Boltzmann constant and T is temperature in Kelvin. And since gases have no favorite direction, each axis x, y, and z gets an equal share of energy, half kT each. So yes, your gas molecules are energy billionaires, but very fair ones. They share equally in all directions. Now let's talk about something really cool, degrees of freedom. Don't worry, this isn't philosophy. In physics, a degree of freedom is simply one independent way in which a molecule can move or store energy. If it can only move along a line, that's 1 degree. If it can move in a plane, 2 degrees. And if it's free in space, 3 degrees of freedom. A single atom, like helium, can only translate, that is, move back and forth in 3 directions, so it has 3 degrees of freedom. And here's the golden rule, each degree of freedom gets an equal slice of the energy pie, half kT per molecule or half RT per mole. So more degrees of freedom mean more ways to hold energy, just like more bank accounts mean more ways to save money. Now, not all molecules are as simple as helium. Some can do a lot more than just move, they can spin and even vibrate. Take oxygen, for example. It's diatomic, 2 atoms joined together like a dumbbell. Besides moving in space, that's 3 translational modes, it can rotate around to perpendicular axes, adding to rotational degrees of freedom. That's 5 in total for a diatomic molecule. But if the molecule can also vibrate, like a spring stretching and compressing, then it has vibrational energy too. The total energy becomes the sum of translational, rotational, and vibrational terms, half mv squared plus half I omega squared plus half ky squared. In short, molecules don't just move, they dance, they spin, and they bounce, each dance step storing energy in its own unique way. Plus, now, vibrations are special because they have 2 parts, kinetic and potential energy. When atoms in a molecule vibrate, part of the energy is in their speed, kinetic, and part is in the spring-like stretch of their bonds, potential. That's why each vibrational mode contributes to halves, 1/2 kT for kinetic and 1/2 kT for potential, making a total of kT. However, vibrations show up only at higher temperatures because it takes extra energy to make atoms stretch and compress. So at room temperature, most simple gases like nitrogen or oxygen act as rigid rotators, their vibrational motion is negligible. Now here's the big idea, the law of equipartition of energy. It says, in thermal equilibrium, the total energy of a molecule is equally distributed among all its independent modes of motion. Each translational or rotational mode contributes half kT, and each vibrational mode contributes kT. Mathematically, total energy per molecule equals F by 2 times kT, where F is the total number of degrees of freedom. This elegant law, first proven by Maxwell, tells us that energy doesn't play favorites, it's shared equally among all available motions. So whether your molecule is flying, spinning, or vibrating, each motion gets an equal slice of thermal energy. Let's see how this law actually works in practice. A monatomic gas like helium or argon can only translate, 3 degrees of freedom. So, its average energy per mole is 3 by 2 RT. From that, the molar specific heat at constant volume, Cv, is 3 by 2 R, and at constant pressure, Cp, is 5 by 2 R. Their ratio, gamma, is 5 by 3, or about 1.67. Now for a diatomic gas, which also rotates, we have 5 degrees of freedom. So Cv becomes 5 by 2R, Cp becomes 7 by 2R, and gamma is 7 by 5, that's 1.4, close to the value for air. If the molecule vibrates too, we add 2 more degrees, giving 7 total, and gamma drops further to about 1.29. So the more complex the molecule, the more ways it can store energy, and the smaller its gamma value becomes. Alright, let's quickly derive specific heat from the equipartition principle. For a monatomic gas, total energy per mole, U, equals F by 2 times R times T. Here, F equals 3. So, U equals 3 by 2 RT. Differentiate both sides with respect to temperature. Do by dt equals 3 by 2R, that's our Cv. From the ideal gas law, we know Cp minus Cv equals R. So Cp becomes 5 by 2R, and the ratio gamma equals 5 by 3. And there you go, the entire behavior of gases captured in a few simple fractions. Beautiful, isn't it? So, what's the big picture here? The law of equipartition of energy tells us that at thermal equilibrium, every molecule gets an equal energy share for every motion it can make. Monatomic gases only move, diatomic ones spin too, and polyatomic molecules, they move, spin, and vibrate. This principle connects microscopic motion to macroscopic quantities like specific heat and gamma, the heart of thermodynamics. So next time you hear that air heats up when compressed or cools when expanded, remember, it's just molecular energy shifting between different degrees of freedom. That's the beauty of physics. It turns invisible motion into measurable reality. Alright, that wraps up today's session. I hope you enjoyed this molecular journey. See you next time when we uncover how these same ideas help explain the specific heat of solids. Until then, keep wondering, keep learning.